So let's begin. So we're just doing a little dive into redox reactions. Shouldn't be an issue, right, or a problem. But if any issues arise, just let me know. So before we start now, I always like to ask you guys questions. Hopefully, you guys, over time as we do more and more sessions, you guys will become more acclimatized to just answering the questions. But I'm gonna ask, what is redox? What does redox mean to you? Let me just ask that. Should be a really simple question.
It's a reaction where reduction and oxidation occurs.
Okay, so it's a reaction with where oxidation and reduction occur. So when we look at things like phosphorylations, photophosphorylations, when we look at things like combustions, when we look at things like displacements and disproportionations and stuff like that, those types of reactions that we would have looked at in CSEC and some amount of Cape Biology Unit 1, right? So a lot of these types of reactions that we've encountered are all redox reactions. So let's just do a little brief overview of it, right? So an oxidation reduction, or what we call a redox reaction, is a type of chemical reaction that involves the transfer of electrons between two species. An oxidation reduction reaction um is any chemical reaction in which, let me just let that person in. Okay, any chemical reaction in which something is oxidized, right? Something is reduced, and in which oxidation number changes, right? So once the oxidation number changes on a specific species, we are safe to say, or we can safely say, that an oxidation reduction reaction has occurred, all right? General redox reactions, right? So whether it be photosynthesis, respiration, combustion, corrosion, rusting, all of these types of reactions are all oxidation reactions, right? Life itself will not, I couldn't say will not, but life itself could not have existed in any way, shape, or form without oxidation reduction reactions, right? May not be in the way that we know of it now, but they couldn't exist without these types of reactions, right? So let's have a look at this. Oxidation is complete loss of electrons, and reduction is complete gain of electrons, right? So when I speak about complete here, we don't generally mean that all electrons, right, are moved. So before I do that, let me just edit this real quick. Because as you guys know, I always edit the PowerPoints, so it makes a little bit more sense for you. I'm not gonna go through saying complete, because when we talk about complete, we're talking about of all the electron transfers within the reaction, right? The net flow of electrons is either loss or gain. But we're not gonna talk about that right now. Right? It's a little bit too much. So generally, oxidation is loss of electrons, reduction is gain of electrons, right? For example, in this reaction here, right? We're looking at the reduction of zinc, right? So, well, is it the reduction of zinc or the oxidation of zinc? Let me ask that. Is zinc being oxidized or reduced?
Oxidized
Oxidized. Why? Why do you say that?
because it lost two electrons.
Because it lost two electrons. Okay, lovely. Right, and we can also see that it increased in oxidation number. All right, so we're seeing that zinc lost electrons here, right, and hydrogen has gained electrons, right? So we're seeing it here. So this reaction is an oxidation, it's a redox reaction, right? And we have the two half equations here, right? So showing the oxidation and the reduction, right? Everything there should be straightforward. Oxidation is an increase in oxidation number, and reduction is a decrease in oxidation number, right? So we're looking at elemental iron reacting with copper sulfate to give, a displacement reaction. As I said before, displacement reactions are redox reactions as well. So iron displaces copper, the more active metal displaces, right, to create the ferrous sulfate or the iron sulfate, and we have copper, right, elemental copper meaning. So in the course of the reaction, the oxidation number of iron increases from zero, which is, we know that anything in its main elemental state is zero, right? It increases from zero to 2 plus. All right, so 2 plus here. Well, plus 2, I must say. Plus 2 there. All right. Remember that the sulfate ion, all right, is always 2 negative, right? It's oxidation. Well, let me put that there. Its oxidation number is 2 negative, right? Or sorry, negative 2. Let me just make that a clear distinction, right, before I move on. Charges are written like this, and oxidation numbers are written like this. So this is the charge, and this is the, well, let me not do that. Do it like that, and this is the ox number, all right? So that's how we write it. So SO42 negative has an oxidation state of negative 2, all right? So it's just the signs that flip really. So we have that here. So we're seeing that iron is increasing from 0 in this state to plus 2 there. The oxidation number of copper decreases from plus 2 in this state to 0, right? So we're seeing here that what, okay, let me not answer that yet. Can you guys just let me know what is oxidized in this case? What is oxidized and why?
Copper because it lost 2 electrons.
Copper is oxidized because it lost 2 electrons. Interesting. Wait, we're not talking about that type of definition. We're talking about the oxidation number definition, right? So as it relates to oxidation number, right, we see the definitions on the screen and we see the explanation and the reaction, right? So what is oxidized in this case based on oxidation number?
Fe.
The iron. Why do you say the iron is oxidized?
Yeah, the iron.
Okay, go ahead.
For increase.
Because the oxidation number is increased, right? Really, really simple. So that is it. So it's really, really simple here, right? So oxidation is the increase in oxidation number, reduction is the decrease in oxidation number. Oxidation is the gain of oxygen, and reduction is the loss of oxygen, right? So we're seeing here in the acetaldehyde, right? We add oxygen to acetaldehyde to produce this, you know, acid, right? Which acid? We type of methanoic acid here, right? So we have this type of reaction, right? The syllabus doesn't specifically ask us to look at it in terms of oxygen gain or oxygen loss, but I think that every single soul should understand these definitions, so you don't waste. If you have like a reaction in which oxygen is being added, so you don't sit around trying to figure out what's happening or what's going on looking through oxidation numbers. You can immediately know that it's an oxidation reaction or a reduction reaction, or see which is being oxidized or which is being reduced, right? So if you understand all four definitions, sometimes as you see anything adding oxygen, you just know immediately oxidation reaction, right? So something like that. So these definitions are used in cases where oxidation number and the loss and gain of electrons are not clear. As you can see here, there are not two species here. It's plus what? There's nothing else, right? So since that is not clear, it's not easy to discern, right, change in oxidation states or the loss or gain of electrons. We can simplify it by saying anything that oxygen is added to, right? We really call it an oxidation reaction, right? So this is oxidation specifically, right? So oxidation is the gain of oxygen, or reduction is the loss of oxygen, right? Here we also have oxidation, right, being the loss of hydrogen in a molecular compound, and reduction being the gain of hydrogen in a molecular compound. Here we have the reduction of acetaldehyde to produce an alcohol. Right, you guys won't look at these reactions until unit 2 in depth, right? But just giving examples of what we mean by these four definitions, right? So we have the reduction there. Right? So when you look at stuff like the formation of pyruvate, um, the formation of pyruvate, specifically in glycolysis, right? Or when you're looking at something like the formation of alpha ketoglutarate within the Krebs cycle, stuff like that, right? You will see the movements of hydrogens, right, and stuff like that around these biological systems, and note that reduction reactions or redox reactions, in a sense, are really important for life's processes, right? So the simple addition or subtraction of hydrogen from a compound can be described as either oxidation or reduction. Right? So it's just something like that. Not just, I don't really want to just give you guys all the definitions and stuff like that, but I want you guys to gain an appreciation for the topic. Because once you have an appreciation for the topic, everything gets a little bit easier. All right? So we have examples there and not just writing the definitions. Okay? Everybody's fine with those four definitions? Oxidation is the loss of electrons, reduction is the gain of electrons. Oxidation is the increase in oxidation number, reduction is a decrease in oxidation number. Oxidation is the gain of oxygen, reduction is the loss of oxygen. Oxidation is the gain of hydrogen, specifically in a molecular compound, and reduction is the oxidation is the loss of hydrogen in a molecular compound, and reduction is the gain of hydrogen in a molecular compound. All right? Any issues with those definitions? Everything is fine? Any issues at all? At all?
It's
Go
good,
ahead.
sir.
All right, it's good. I think somebody raised their hand. I'm not sure, but let me know if there are any questions. All right. So we're moving on. We must understand. Sorry, let me just say this. We're just going to be recapping what we did in CSEC, right? So the rules for assigning oxidation states, right? The oxidation state of an element corresponds with the number of electrons, right, that the atom loses or gains or appears to use when joining with other atoms in compounds. In determining the oxidation state of an atom, there are several guidelines that we need to follow, right? These are several guidelines, right? It's six here, but it's several guidelines. So the free elements in their uncombined state, right? Each atom has an oxidation number of zero, right? In their uncombined state, right? So we look at elements like hydrogen, bromine, sodium, beryllium, right? If they're in their uncombined state, right, they are zero, right? Oxidation state is zero. Number two, the monatomic ions. And as I go through it, and if you have any questions, you just let me know. The monatomic ions have oxidation states equal to their charge. So any ion that is monatomic, right, it alone bears a charge. That charge is equal to its oxidation number. So the lithium ion, right, it has a plus charge there, therefore its oxidation state is +1. Barium's second, barium's ion, right? The second degree ion here, the 2 plus ion, has an oxidation state of +2, right? Iron's 3 plus ion has an oxidation state of +3. Iodine's ion specifically, it's an iodide ion. It's really, really simple, right? They're halogens, so they're generally going to have oxidation states of -1, right? Oxygen specifically has two negative, therefore its oxidation state is -2, all right? So it's really, really simple there. So it says, it continues to say that alkali metal oxidation numbers is +1, right? We know that already. We understand that. Can we appreciate that? Do we know why alkali metals have oxidation states of all +1 generally? Where are the alkali metals on the periodic table?
Group 1.
Group 1 elements. Wonderful. So group 1 elements tend to form these um +1. All right, these type of 1 plus ions specifically. So the group 1 elements that we know of, what are those group 1 elements? These the alkali metals that we know, what are they? When you see them, you should be able to know their oxidation states immediately. So your group 1 metals like lithium, all right? So lithium, sodium, potassium, rubidium, right? Looking at cesium and francium, all right? So look at these elements. They're all in group 1 of the periodic table, and they all have oxidation states of generally +1, all right? So those are the group 1 elements, our alkali metals. And we continue to see that our alkaline earth oxidation states are all +2, right? So our alkaline earths are group 2 metals. So beryllium, magnesium, we have calcium, we have strontium, also we have barium, and we have radium. All right. So these are all going to be our plus 2. Really, really simple. All right. So those are alkaline, right? When we look at the other compounds like or group 13 element, they're going to be a little bit different, right? But we can say that aluminium, all right, being a metal there would have a plus 3 charge, right? In all of its compounds. That's an interesting thing there, all right? Oxidation states can change depending on the compound in which the atom is bonded into. Aluminium tends to be 3 plus 3, right, in all of its compounds. Oxygen's oxidation state is -2, except when in hydrogen peroxides, right? Um, or just the peroxide ion where it is 1 minus, right? Just reviewing these things, hydrogen's oxidation number is +1, except for when bonded to metals as the hydride ion. Because we know the hydrogen ion specifically, but you also have the hydride ion, right? So when it's bonded in its metal hydrides, right, it would have an oxidation state of -1, right? Fluorine has an oxidation state of -1 in all of its compounds. All right, so fluorine is always -1. Our halogens, chlorine, bromine, iodine, have negative oxidation numbers when they form halide compounds. All right, so halide compounds meaning any compounds that include halogens, right? When combined with oxygen, they have positive numbers. Interesting. In the chlorate ion, we have chlorate here. The oxidation number of chlorine is +5. It is +5, and the oxidation number of oxygen is -2. So notice that when the halogens bond with a chalcogen like oxygen, right, they are going to bear positive oxidation states, right? Then 6, in a neutral atom or molecule, the sum of the oxidation numbers must be 0. In a polyatomic ion, the sum of the oxidation numbers in all the atoms in the ion must equal the charge on the ion. So in short, the oxidation states in a compound must equal the charge. So if the charge is 0, it's neutral, it should be 0, right? If the charge is -1, right, or 1 minus is the charge, then therefore everything should add up to give you 1 minus, right? So that's what generally works. Any issues or concerns here, by the way? Any issues?
Also,
All right. If there are any issues along the way, though, let me know. All right. So even if I pass a slide, you can just ask me a question and I'll go back to the slide and go over. All right. So let's move on. So this is another set of rules. It's generally the same rules per se, but it's another look at it. It's much more compact and it has examples here. Right. So it should just be another set of rules. Okay. So that should be fine. Now let's do some practice. Give me the oxidation states, right, of both atoms within these compounds, right? So in this session, we're just gonna be doing the first column here from A to G. I'll be doing A to G, right? And then you guys can try out H to U, all right, on your own timing there. So have a go at some of them, right? At A. Let me see. I'm going to ask for persons to volunteer to just give me the answers. All right, so Candice, are you here? Candice.
Yes, sir.
Hi, Candice. Could you try out A, please? All right, so I want you to try out A. Michaela, I want you to try out B. Shanique, you could try out C. Azrael, hopefully I'm pronouncing it correctly. You can try out D. Right? Please remember what I gave you guys to try out. Laquanda, you can try out E. should be fine for you. Ariana, right? Diamond, Ariana, should you try out F? And for G, let me just see if I can. Anaya, could you just try out G? All right. So just remember what I told you guys to just try out. All right. So I want you guys to give me the oxidation state of both of the species in those compounds. All right. I'm going to give you guys 2 minutes. Well, should I give you 2 minutes? 1 minute should be enough, but I'm gonna give it 2 minutes anyways. So let me just set the timer, 2 minutes. When you're finished, just drop a one in the chat, by the way, for the persons I asked. But I want everybody to try it. All right, so just try them. Just assign the oxidation state. So 2 minutes starting now.
Assign the oxidation what?
States.
Repeat.
Assign the oxidation states. Can you hear me?
Oh, oh, oh.
Okay, no problem. So for this, you're just going to find the oxidation state of sulfur and of oxygen within the compound. All right, should be fine. Mm, 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 mm. Doo, doo, doo. Vanadium. All right, you guys have 1 minute remaining. All right. Okay, so two persons have finished so far. Three, okay. Ariana, hopefully you'll be able to finish. Okay. All right. Guys are doing well. 20 seconds remaining there. Just to finish up to make sure that you know you're confident about the answer. 10 seconds. All right. So a number of persons are finished. Candice, how did you fare with number one?
Was I supposed to break down the reaction?
No, 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 not at all. All right. It's just looking at the oxidation states in the
The
compound specifically.
SO3.
For SO2, it's SO2. You attempted it though, right?
I'm trying.
Okay, no problem. Well, B, could you go, please? The person who got B.
Calcium is +2 and fluorine is -1.
So we have +2 and then fluorine is -1, right? So we have rules there, wonderful. We would generally already know that any group 2 metal would always be +2, and fluorine always is -1 in all of its compounds, right?
Sir,
Go ahead.
why don't you just ask for the oxidation number? That's what they call it in school. I didn't have to work that out. SO2 is -2 and oxygen is +6.
Okay, give me a moment before I go there. All right, so that is that there. For the sulfur you said, right? So you're saying, Candice, now you have one sulfur atom bonded to two oxygen atoms. The oxidation number of sulfur in this compound is
-2,
-2, all right, and oxygen,
+6.
you're saying it's +6. All right, interesting. Okay, so we have the sulfur dioxide compound. Hmm. How did you get the +6? Let me just ask that.
That's the number that where well, I don't remember the number what they use, but I know it's negative. It's positive 6. I am sure it's positive 6 because when they
Hmm.
ask us for the oxidation number of oxygen, it's always positive 6.
Interesting. Okay, so no problem, no problem. But what we have here as a general rule for oxygen is that oxygen's oxidation number is -2, except for when it's in hydrogen peroxide and in its peroxide ion. So judging by the fact that it's not bonded to hydrogen here, it should be -2. I'm not sure if the positive 6 comes
So,
from a different topic, but go ahead.
so SO2, what's the final number for SO2 altogether?
Oh, SO2, the oxidation, there's no oxidation state for the compound itself, right? Because the compound itself would have a charge, right? And SO2 is just a neutral charge, no charge. Therefore, both of the oxidation states need to add up to give you zero, right? So both oxidation states
So
must add up to give you zero.
it would be positive 4.
+4, right? But if this is +4, right, then we won't get zero, will we?
No, no, not
Mm-hmm.
there.
Or
I'm
+4 for the
talking,
sulfur.
yeah, it
So you're
would
saying
just be,
this is +4, and then this would be -2. That's what you're saying, and that should give you zero, right? Right?
I'm trying.
Okay, no, it is, right? It's fine actually, because what's happening here is that there are actually two oxygen atoms, therefore the overall thing would be -4, right? And then that means that the sulfur would have to give +4 in order for everything to be zero. So it is fine, all right? It is fine. So this is fine here. Thank you for attempting it, all right? So let's have a look at this. Everybody's fine with this so far? Everybody's great so far with this.
Hold on, sir. So for that, S is 4 and O is -2, yeah?
Yeah.
Okay.
All right. So we're
So
looking at
wait, wait, wait. I have
Go
a
ahead.
next. I have another question.
Mm-hmm.
In what reaction does the oxygen turn positive 6? Because I know I saw it somewhere.
That's interesting. Positive. I don't think oxygen can be +6. Okay, I'm not sure if you're mistaking something different for oxygen, right? It could be that you may be mistaking something, right? But I am not. I can't recollect oxygen being having a +6 state. I can't recall that, right? So if I recall it, all right, then I'll let you know. But I can't recall that at the moment. All right. So in the interest of time, let's have a move on to C. The person who got C, go ahead. PO3 3 negative. Go ahead. The person who got this, where are they? Okay, so go ahead. Okay, let me see now, Shanique. So you said that phosphorus is, ooh, that's, those are, okay. So your values are not wrong. Okay, your values are not wrong, but your answers are wrong. What you need to do is put those, you know, those charges, right, differently, right? Okay, so you're saying that phosphorus, it's 3 negative. The oxygen already has a charge of 3 negative. I'm not sure what that means. I'm confused. Can you explain what you're saying, Shani? Hopefully it's Shani. I'm not getting that. Could anybody explain what she's trying to say? Because I don't understand that. See if you could rephrase it. So is the oxidation state for them both -3? No, it cannot. Okay, so let's have a look at this, right? Well, no, it cannot. So we're saying that the charge, go ahead.
Accident- So I think she's accidentally using the three negative as an overall charge for the O3.
Oh, no. Okay, so we're three negative, right? Is the charge of the entire thing, right? So it's a charge on the entire thing. So that means that the oxidation state, right, must equal -3, right? It's oxidation state or oxidation number, right? As some persons say. When I say oxidation state, I mean oxidation number, right? So that's what we're looking at. So the approach to these polyatomic ions is that when we see this, we know that both of them must add up to -3. The rule of oxygen generally states that oxygen two is -2, right? And there are three oxygens, right? So if you times that by three, right, we're gonna have what? Minus what, 9? Is that it? Oh my gosh. -6. LOL. Alright, so we're gonna have that. And then we're going to have no the fact that it's -6, right? And we need to get -3 or -3, right? This would have to give us a positive charge that would allow for everything to give us, a -3. Make sense so far?
Yes, sir.
All right. So what is the charge that phosphorus must possess in order for us to have -3 as our answer? What is the oxidation state that it must possess?
+3.
+3. Right? So it's +3. So phosphorus is +3 and oxygen would be -2. And it would give us the charge on the ion. All right? So that is generally the case. Make sense? Any issues there?
No,
Hopefully,
sir.
okay. Hopefully we'll be able to finish in time. All right. So we have that there. Moving on to the next one, PO43 negative. So what is the difference here now? So the person who got this, go ahead. What is your answer for this? Hmm.
For phosphate, the charge is -8, and for oxygen, the charge is +5.
Oxygen is +5. Interesting. Let me check something. All right, because I want to know whether or not not saying that anything is bad, everything is fine, right? But let me just check something real quick. Oxygen's oxidation number is -2 except for when it's bonded in hydrogen peroxide or as a peroxide ion. I'm not sure, Just let me know if I'm firmly disillusioned, right? Because I don't remember oxygen having a positive oxidation state ever, right? So what we have to do is use the rules there because I understand what you're saying. It's an answer, right? But it doesn't seem like the right answer. What was the answer again? Just let me know what your answer was again.
-8 and +5.
So -8 on the phosphorus and +5 on the oxygen.
Yeah.
All right. So let's see if we could use the rules because the rules that we use, right? We commit them to memory, so we just use them. So oxygen by itself, we know that oxygen on itself has a 2 negative charge, therefore its oxidation state is -2, right? So one oxygen is -2, right? And there are four of them. So the overall oxidation number that oxygen contributes to the compound is
Wait,
what?
wait.
Go ahead.
No, sir, my bad. The phosphorus has +5 and the oxygen has -8.
Okay. So +5 and -8. All right. So that looks a little bit better. So we're gonna have -8 there, right? And in order for us to have a -3 as the answer, right? The phosphorus needs to contribute something to give us -3, which is +5, right? To give us that -3 there, right? So this is right. So you just misthrown that the answers. So that's fine. All right. Remember, at any point in which anything becomes a little bit shaky for anybody in this entire session, let me know. Go ahead.
Sir? All
Go
right,
ahead.
so I see how to get the 5 and the 8, but could it also be 5 and -2?
Uh,
Seeing that you type the -2 by the 4 if you get the 8.
oh yeah. Thank you. Okay. Thank you for that. Thank you for that. Please. Okay. All right. So it's actually -2, right? So the person who answered before it's -2 are two negative as the answer, right? So -2 is the answer, right? So -8 is the overall charge, but the oxidation state of oxygen is -2, right? That almost ran away from me. So your answer is right as it relates to oxidation numbers and providing the answer, right? But when you look at the overall oxidation state that all the oxygens give you, right, you try to reduce that back to what one oxygen is worth, right? So that would be -2. All right, thank you for that reminder. So the person who gave that answer, change your oxidation state of oxygen back to -2, because that's what the oxidation state of a single oxygen is, right? The person who got the peroxide, let's go.
Um, Hydrogen is +1 and oxygen is -1.
Lovely. All right. So that is the answer because oxygen is always -2 except for in peroxide, which is -1. So that is the answer there for the oxidation states of both. All right. So that should be fine. Moving on. Remember, if you have an issue, just ask. All right. For okay, let's look at this compound now. NaSiO4. What are the oxidation states? Go ahead for the person who got F. Mm-mm. Not hearing somebody respond. All right. Not hearing somebody respond. I'm not sure.
Can I answer?
Oh, go ahead. Then you can go ahead.
Sodium will be +1, silicon will be +7, and oxygen will be -2.
All right. So that would be -8 plus 7 plus 1. Fine. All right. So this is right. Complete. Fine. Right. So neutral molecule, all of this would give us 0. All right. And for potassium permanganate,
Potassium would be +1. Mana- man- the oxygen would be
manganese.
manganese would be +7, and the oxygen would be -2.
All right. So manganese would be +7, and you guys would have already known that manganese, when it has its +7 oxidation state, it is purple. All right. So you guys would already know that. And when this is reduced, right, through different types of reactions, right, it will change color. Right. So we know those. So that should be fine. So constructing half equations. Let's see if we can do this in 20 minutes. Right, just seeing are there any issues or questions with how we find the oxidation states and assign oxidation states here? Any issues? All right, in the interest of time, I'll move on. Let's see if we can knock this out in 20 minutes. All right, so I urge you to just focus for 20 minutes. So constructing half equations, dividing and combining redox reactions. That's what we're all gonna be talking about here, right? So an electron half equation is what we have here. So we have the copper 2 plus ion reacting with magnesium, right? And then we have now the copper in its elemental state, and the magnesium is now the ion, right? Just showing this really simple exchange of electrons here, right? So we have this here. This would be, let me just label it A and B. This is A and this is B. What type of reaction is A? Is it oxidation or reduction?
Oxidation.
Oxidation.
Oxidation. Wonderful. That means that B is reduction, right? So the half equations show with the electron half equations, all they show is the movement of electrons generally, right? So if A is oxidation, all it's showing is that magnesium before the reaction is complete, the magnesium was fine as elemental magnesium, right? And at the end of the reaction, we produce two different things. We have magnesium as a 2 plus ion, and we have two electrons being produced. So it shows that there's a loss of electrons from magnesium. And for copper as well, we start out with a copper ion and two electrons, right? And the two electrons are added to the copper, creating elemental copper, showing that this is a reduction, all right? So remember all of that. Oil rig or Leo the lion says grr, right? Any other one you want to use, right? Just remember that. And you have Leo and grr, all right? So there are two of them, but we tend to use oil rig here in the Caribbean, right? So we have that there. So everything there should be fine. So once there's an issue, just let me know. All right. So let's seek to balance these reactions now. You see, when we'll be balancing these reactions in like C-seg, right, all we do is just move around the electrons and balance these, right? But right, right now we're just gonna be moving up in a little bit more complexity, all right? So one method used to balance redox reactions, which is covered in CAPE as well, is called the half equation method. And this method, right, in this method, right, the equation is separated into two half equations, one for oxidation and one for reduction. Makes sense. Because this is an example of a half equation, right? The two half equations here, and we can use it to balance, right? But this is already balanced. So let's have a look at this. The half equation method to balance redox reactions in neutral aqueous solutions, right? So the first step to balance any redox reaction is to separate the reaction into its half reactions, right? The substance being reduced will have electrons as reactants, important, and the oxidized substance will have electrons as products. Makes sense. Sometimes it's necessary to determine which half reaction will be oxidized and which will be reduced, right? So which one will be the oxidation and which one will be the reduction reaction. In this case, whichever half reaction has a higher reduction potential will be reduced and the other oxidized, right? So we're going to be looking at those type of oxidation reduction potentials in module 2. All right, but let's have a look at this. Step 1, all right? We're starting with this general thing here, right? Which equation is this? Do. Mm-mm-mm-mm. Right? We're looking at copper and iron reacting, right? So first, what we do is separate the reactions, right? By searching, right, for the reduction potential or whatever, right? But we haven't really gone into that yet. So it would be really simple to see what is reducing and what is oxidizing, right? But in this case, what they did was separate an equation into both of its half fractions. So you have your oxidation and here you have your reduction, right? So the copper reaction has a higher potential and thus is being reduced, right? And iron is being oxidized, so the half reaction should be flipped, right? So we have that there, and looking at the yields here now, right? So iron is being oxidized, so we're going to have it flipped here, right? Copper is being reduced. Everything makes sense so far? It's just looking at it stepwise. Right? So we
Yes, sir.
have, okay, wonderful. So we have the half reactions like that. Then what we do now is balance the electrons in the equation. So in this case, the electrons are simply balanced by multiplying, right, that the copper reaction, half reaction, right, by 3 and leaving the other reaction as it is. Makes sense. Because in this reaction, we have 3 electrons, and up here, okay, let me just use this specifically. Right? Let's look at this part, right? So in this reaction, we have 3 electrons here, and in this reaction, we only have 1. So we need to times this by 3 in order to equate the number of electrons, right? So that's what they did in step 2. They times this equation by 3 in order for the 3 electrons to be there, all right? Then a lot of persons do recommend that you add the equations together, right, and then cancel out. But I do recommend personally that you cancel out before you add the equations together. So once you have the electrons being the same number, we cancel both of them and then just add the remaining things to give us that, right? and then we just put everything together. So we put reactants together and we put products together. All right. So notice that we take this now and put it here. We took this and put it here, right? All we do now is just add in everything. We took this and put it here. We took this and put it there, right? After we cancel the electrons. So no more electrons should be left in your balanced equation, all right? So it's as simple as that. Any issues?
No, sir.
All right. Any issues from anybody else? We separate into half equation.
Okay.
Okay, wonderful. So separate into half equation, we identify oxidation reaction, reduction reaction, right? Equate electrons, cancel, then add them. That is all, right? That is in neutral reactions or neutral solutions, right? So in CSEC, what we did was a lot of neutral solutions. There was always neutral solutions because the only thing we balanced was electrons, right? But let's look at acidic aqueous solutions. Now, acidic conditions usually implies that the solution has excess proton concentration, hence making the solution acidic. So balancing starts by separating the reaction into half equations, right? That's always what we do because it's a half equation method. However, instead of immediately balancing the electrons, we balance all the elements in the half reactions that are not hydrogen and oxygen, right? Then we add water molecules to balance any oxygen atoms. Next, we balance the hydrogens with protons, and then we balance by scaling electrons, right? And then canceling, then adding the two reactions. So there are no extra steps, and we're going to go through it in depth, right? So we're going to be balancing chromate reacting with nitrous acid, right? To give us this chromium ion and nitrate ions, right? So this is the equation in which we'll be balancing, right? So what's the first step again, guys? That's the first thing we do.
Separate them into half equations.
Wonderful. We separate them into half equations. So we just broke up that reaction, right? So we cut them into two here, right? Separate them into their basic half equations here, all right? So let's have a look at this now. So we cut them like that, right? Then now we have the two half equations and then we balance the elements, right? Other than oxygen and hydrogen. So it's going back here now. We don't know the electron transfer now, right? It's an acidic solution, so we don't really do anything like that, right? So what we do now, we just cut it into two, right? So going back to this reaction, we just have the chromates producing the chromium, right? And we have the nitrous acid producing the nitrate. So we just cut it up into two, right? So chromate produces the chromium ion, and nitrous acid produces the nitrate, right? And then after that now, we balance everything that is not oxygen and hydrogen, right? So balance everything that is not oxygen and hydrogen, right? So we're starting from there. So in this case now, the chromium has two chromium atoms, right? And here now we only have one chromium, right? So what do? We add the two there to balance the equation. Make sense?
Yes, sir.
Right. And here now for the nitrous acid, everything should be fine here, right? We're going to be looking at how we balance this now. So we balance everything that is not oxygen and hydrogen. In this equation now, the thing that is not balanced is the oxygen. The oxygen is not balanced. So how do we balance the oxygen? Can anybody tell me? We balance the oxygen by
Adding water.
adding water. Wonderful. So we add water to balance the oxygen. The chromium reaction needs to be balanced, right, by adding 7 water molecules, right? And the other reaction needs to be balanced by adding 1 water molecule. So in the beginning we had 7 oxygen atoms here, right? But we had no oxygen atom. So what we do now, we add 7 water molecules because now we have balanced amount of oxygen on both sides. And in the nitrous acid, we had 2 here, right? But 3 over here. So we add 1 water molecule so we can get that singular oxygen there. So everything can be balanced. All right? Any issues so far? If something is not clicking, let me know. because I know I'm moving a little bit fast, right? So we balance the oxygens now by adding water. Now there's an issue. We do not have equal amounts of hydrogen on both sides of the reaction. So how do we balance the hydrogens?
Add H plus ions to the opposite side.
Love that. We add protons to the solution now. Now, in this case, now let's look at this side of the solution now, right? We know that we have 7 water molecules, right? And we have 2 hydrogens per water molecules. Therefore, we have 17, we have, sorry, 14 hydrogen over here, right? In order to balance that, we had 14 protons on this side to balance out the hydrogen, right? And for here now, that's what we do. We have 1 hydrogen here, we have 2 hydrogen here, so we need 3 here to balance out everything. So we add our hydrogen ions, beautifully balanced. Any issues? Any issues whatsoever?
No, sir.
All right. Just wondering if you can following. All right, so we're following. Step 5, we balance the charges of each equation with electrons. So now we add in not only the first we add in the water to first we balance the equations, right? For all elements that are not oxygen and hydrogen. Then we balance oxygen with adding water. Then we balance hydrogen with adding protons. And now we must balance the charges because there's more charge on one side than on the other side. That can't happen. That means there's an electron imbalance. And now we add electrons to balance the charges. All right? So the chromium reaction has 14 plus 2 negative equals 12 plus, right? That's a charge on that side, right? The right hand side. So on the left side, we must add, right? Plus 6, right? We're going to have plus 6 there. So on the right hand side, we have that, right? So on one side, we have the 12 plus, right? The left hand side. And on the right side, we have 6 plus. So to balance, we add 6 electrons to the left side. Not sure if that makes sense yet. Let's look at what's happening here. Let's look at it, right? On this side, we have 14 protons, right? So that's a charge of 14. And then we have 2 minus here, right? So that would give us what? That would give us a 12, right? So the charge over here is positive 12, right? Or 12 positive. Let me write it in chemical nomenclature, right? On this side now, we only have what? What's the charge over here? We have 6 plus because we each chromium ion, right, is 3 plus and we have 2 of them. So it's 6 plus. So in order to balance now, we add, right, 6 negative electrons to this side. So we add 6 electrons here in order to balance it out. Everybody sees that?
Yes, sir.
All right. So here's the 6 electrons that we added there. Right? And for the nitrous acid, right, we look at the charges and everything, and we decide that we have to add, right, 2 electrons on the right hand side to balance it. Right? What do we do next? Can anybody tell me what we do next?
Cancel.
No, you can't cancel. Notice that our electrons are not the same. We don't have the same number of electrons. So what do we need to do?
Yeah. The number of electron.
You equate the electrons. All right. So here now we have to equate the electrons. So we times this equation by 3, right? Because we have 2 electrons, and we need it to have 6 electrons. So we just times that equation by 3 for us to get 6 electrons here. So this is equating the electrons. Everything's fine here. So you equate everything, by the way. Some persons think saying just times the electrons by 3. No. If you times in something, everything have a times. So it's just like how you do simultaneous equations because redox reactions technically are simultaneous equations. Not necessarily. They have to be disproportionation to be simultaneous. But you guys understand what I'm saying. So you have to times that by 3, all of the equation by 3 in order to get these 6 electrons here being the same as the 6 electrons there. And no, we cancel. We cancel electrons. So we start by canceling the electrons. That 6 cancel that 6. All right. What else do we cancel? We cancel the water as well. So this 3 water there, right, cancels out, right, there. And when we cancel that 3 water, we end up with 4 molecules of water over here, 4H2O. And then we must cancel the hydrogen, right, the protons in solution, right? So in cancel, we know what we're going to have. So let's have a look here. This is what we're going. Let me just do this first. Cancel the 9 there from the 14. We should get what, 5? 5 protons, right?
Yeah.
So we should have 5 protons, 5. So every single thing that we add along the way, we equate the electrons, then we cancel everything. That is how we do acidic solutions, right? We equate, then we cancel. We do not equate the protons. That is a big no, right? We do not equate the water. That is a cardinal sin. The only thing we equate is the electrons, right? So you see, we add water, we cancel water. We add protons, we cancel protons. We add electrons, we cancel the electrons. And we end up with this beautifully balanced equation here, right? Wonderfully balanced, right? It's balanced not only in the participating ions, but it's also balanced in oxygen, it's also balanced in hydrogen, and it's also balanced in charge. This is how we balance an equation, right? So we don't just move around numbers anymore and believe that electrons just cancel out whatever, whatever, as C-Sec students do. At CAPE, we operate at a much higher level, right? So this is what we do, right? So that is how we balance equations in acidic as solutions. But what about basic solutions? There will be a difference here. No, we have only 2 minutes left. All right, but basic solutions, let's see how far we can get here. Let me send this. I'm going to send this link into the unit 2 because I have unit 2 now. But we're going to just continue through this until we end. Just let me send a message into the unit 2 group. All right, so bases dissolve in water to produce hydroxide ions in solution. We know that already, right? So we have to follow the same steps as acidic conditions, right? The only difference is that we'll be adding hydroxide ions to the sides, right? To balance, right? The reactions per se. So we add hydroxide ions to each side of the net reaction to balance the amount of protons that exist. That is what we do. That is what we'll be doing, right? So let's have a look at this. Good evening, the unit 2 students. Just give me a moment. Separate the half equations, right? So we separate the redox reaction into its half equations. We're starting with this now. We have silver reacting with zinc, right? And we know that we end up with a silver oxide over here. So how will we actually balance this? All right. So let's start out first now. We'll cut the reaction into two. Right. We have an oxidation reaction, right, and we have a reduction reaction. Right. So we're gonna be looking at that. We balance every element that is not oxygen or hydrogen. Right. So we start out by balancing our silver, but our zinc is fine because it's one zinc on both sides. All right. Everything is fine there. Then we add water to balance the oxygen. Right? So we add the water here to balance the oxygen that is right there. Hopefully everybody is following. All right? Then we balance the hydrogens with protons. So now we add the protons here to balance the amount of hydrogen that is over there. Notice all is going on, Zinc is fine. Because zinc nor oxygen nor hydrogen for balance. And zinc don't balance by itself. Alright? So this is like one of the simplest equations, just balance, right? So we add the protons, we have to balance the hydroxide ion, not sorry, not the hydroxide ions, the hydrogen atoms over there, right? So we add the protons to balance the water, right? Then now we balance the charge with electrons, right? So we know there's a difference in charge on the molecule on the reaction itself. Over here is neutral, right? But over here had the two protons, therefore we must cancel out the charge with two electrons. Simple, right? And in this case now, we must show electrons in the zinc, right? Producing the zinc, elemental zinc here, right? So we can't just ignore the electrons. We must have that there. All right. What do we do next? What is done next, Unit 1?
Cancel electrons.
Cancel it. Okay, but first we must equate the electrons, right? Are they equated? We have two electrons here and two electrons there. So it seems as such. So we will cancel out the electrons, all right? So we're going to end up by scaling the reaction, right? That's what persons tend to describe it as. So we scale it, right? And we cancel out the electrons. But notice that water has only been added to one half equation, right? And hydrogen ions have been only added to one half equation, right? So you can't cancel what is not in the second reaction, right? So let me remove all of that. Electrons are here, we cancel electrons, but we don't have any protons to cancel, we don't have any water to cancel because they're not in both equations. So all we do, we cancel electrons and we put the equations together, all right? Cancel the electrons, sorry, and we put the equations together. So that is what we have, all right? So a beautifully balanced equation. Now all the equations that I see must be balanced, all right. So any redox equation must be balanced. I will not accept any equation that is not balanced to perfection in basic and acidic media. All right. So basic solutions, acidic solutions, those are that is how you balance these reactions specifically, right? And just to show standard potentials, you'll go through standard potentials in module 2, right? But this is generally the different half reaction reduction potentials, right? That you guys will be looking at. So based on this table, I do recommend that you screenshot the table or you wait for me to send the PowerPoint, right? But you guys will be understanding why in our primary reaction where we had the redox in neutral aqueous solutions, we saw that since copper has a higher reduction potential, copper was the one that actually went through reduction, and we flipped iron's reduction to an oxidation. We're gonna understand why we do that, and that's really just based on who has the higher reducing power or who has the higher oxidizing power, right? So we're going to be going through that in module 2. And at the end of the PowerPoint, we just have an example of some common oxidizing agents that you'll actually see more of in Unit 2 chemistry, right? So you'll see more of ozone, right? Well, ozone in higher chemistry for ozonolysis, dichromates, hypochlorites, these are all oxidizing agents. They're wonderful oxidizing agents, permanganate as well, and some useful reducing agents, right, like glucose and ascorbic acid and sodium thiosulfate, and we also have aluminum alhydride, right? So lithium aluminum hydride, right? So those type of things used for reduction reactions and stuff like that, right? So those are some important reagents that you can look at. But that's basically it for redox reactions, right? So that's it, Unit 1. Are there any questions or concerns before I start leading with Unit 2?
Yes, sir.
All right. So